Hey kiddos, it is your teacher, Miss Green. I am still alive, at least on the outside. On the inside is another story. I first just wanted to thank you so much for your patience and your understanding during this time while I've been away. Um, I am a heavy believer that knowledge is power. And the more we know, the more we can kind of handle what life throws at us, and especially engaging in science and, actively observing and taking in data and analyzing and responding accordingly is kind of, what we do. And so, with that being said, I did kind of want to let y'all know what's been going on. As you know, in the past couple months, Ms. Green has had some issues with hearing and hearing well. And so I definitely thought it was something that was like allergy related and not that deep. As Ms. Green would say, it literally ain't that deep. And so with that being said, I went to my doctor's appointment last week on Tuesday, and I found out it is in fact that deep. And so I have gone from having 100% of my hearing in my left ear down to like 40% hearing. And so I am legally deaf now, and it's very sudden and unexplained. And so there's a lot of mysteries around it. I've been undergoing some medicinal and procedural treatments to hopefully try and salvage whatever is left of my hearing. It's been a kind of scary process and kind of a really huge adjustment for me. And so yeah, it's been interesting, to say the least. And, I am going to try my best to keep y'all in the loop about what's going on. I do have many other tests and treatments coming up, specifically to try and hopefully pinpoint what caused this sudden and permanent loss of hearing. Because unfortunately, it's not like, oh, like I listened to something way too loud, or, I jostled some of my ear bones. Unfortunately, it's something that's neural. And so a big part of my testing coming up is going to be like MRIs and just making sure everything in my brain is okay, at least okay in the sense of allowing me to hear. All y'all know that I can be quite quirky and seemingly out of my mind at times, but that's just normal. And so, yeah, that's what's been going on. And so I don't want to worry y'all. I just kind of want to arm you with that information and know that there isn't anywhere else I would want to be than there with you, learning and teaching with you and heckling you and being able to share my passion for science with you. And so just know that this is really kind of uncharacteristic of me. I hate being away, but further that y'all are still on the forefront of my mind, even through this kind of difficult new chapter in my life. And so, yeah, anyways, thank you for listening, I guess, coming to my TED Talk. And yeah, y'all take care. Hopefully see you soon. All right, kiddos. So what we're going to do today is start talking about atomic theory. I know it's been long overdue. I've been trying my best to wait to get into that until I got back to school. Obviously, the universe had other plans for us. So here we are. And so I'm gonna kind of get through the very beginning introduction into atomic theory. And so if you took IPS, this is probably something that might have come up before. This might be kind of the information that might have overlapped in your other science courses. And so as a result, you might kind of have some familiarity with it. And if you don't, that's totally okay. That's why we're doing this now, and why you're taking chemistry now is so you can learn it. And so, yeah, I'm really excited to talk to you about atoms. As we know, we can't trust them because they make up everything. Do you get it? Because they make up everything. Okay, I think I've used that joke before for y'all, but it's still a good joke. And so I'm gonna go ahead and bring up our PowerPoint here, which will be posted on Google Classroom. And so beautiful. So let me go ahead and say view, slide, view. Can I, hello? Okay. So we are going to learn about atomic theory. So our main guiding question here is, what are the particles that atoms are made up of, and what are their properties? And so we've talked very briefly before about how there are subatomic particles, aka things that are inside of atoms, which can be considered particles. And so particles can kind of act as this general sort of terminology to address like individual things grouped together, like photons, for instance, which are our packets of light that we get. And so, as you already know, atoms are going to be the building block of all matter. They're basically like little Legos that piece together everything that we see and don't see, and that exists. It's all made of atoms. And so just like we talked about in class, even solid objects like your desk, a wall, you know, you, for the most part, are all going to be composed of these atoms. And even though they might appear solid to the naked eye, they're constantly vibrating because of sort of how dynamic those subatomic particles are inside of atoms. And so we talked a little bit briefly about the history of chemistry, namely about the different folks that kind of discovered these different aspects of atomic theory and how we know what we know today. And so if we recall, good old Democritus, so he was from ancient Greek times. He actually postulated this idea of the atom called atomos. And so this idea means that the atom is able to be cut up into smaller pieces, and it keeps going until we can cut it no longer, okay? And so the three smaller particles, okay, the three we're going to focus on are going to be protons, electrons, and neutrons. And so you're going to hear that a lot in this unit. And so we'll get into depth as to what those are, what they mean, and how they help us identify an element and how it's going to react. And so a nucleus, you probably heard this before in bio, is going to be an atom's central region where protons and neutrons are found. So the protons and neutrons are in the nucleus. Protons and neutrons are in the nucleus. Protons and neutrons are in the nucleus, okay? So please do not forget. Do not forget. And so, hang on, let me see if I can pop my iPad over. Cool. Oh yeah. This is nice. Okay. So let's say, so here, let's just say this is an atom, nice, beautiful circle, perfect circle. This is going to be our nucleus right in the center, nucleus. And so this is going to be our protons and neutrons. Listen, this is why I teach science and not English. And neutrons. Okay, and so you may have noticed that this beginning of the word looks very familiar to the word neutral. And so that is going to come in handy, okay? Not only in terms of spelling, but understanding sort of its role within our atom. Okay. Let me see. Ooh, I like this ability to have multiple sharing up. All right. And so the size of the nucleus. So if we think about I guess the relative size of the nucleus inside of an atom. What I drew, it looked kind of like the nucleus was fairly big. And so that is just to act as a representation. Obviously, it's not going to be true to scale. And so to kind of give you a better idea of what scale we're working on, imagine a full-size football stadium field, okay? And then imagine one little marble, tiny, tiny marble in the center of that field. So that little marble is going to be the nucleus, and that football stadium is going to go ahead and represent our atom. So to give you an idea of just how much space is within an atom, especially relatively to the size of the nucleus itself, which is pretty cool, in my opinion. Okay. So the nucleus is extremely dense. Doesn't mean it's stupid, just means it has a lot of mass for a small area. Okay. And so when we're talking about mass, we're talking about something called an atomic mass unit, or AMU. And so we know that protons have a mass of 1 AMU. And then neutrons, remember how I talked about the word neutron looking like neutral? Neutrons are going to have no charge, and then they're going to have a mass of 1. Okay, and so we'll talk more about charges and what they mean. Okay, so, but we have protons and neutrons that are in the nucleus, and the number of protons and electrons is going to be unique for each element. And so we'll talk more specifically about what those two things are, and what I mean when I say they're unique, because they're unique in different ways. All right, so let's talk about electrons. So electrons have a -1 charge, and they have a mass of 1/2000th AMU. So for all intents and purposes, we call their mass 0 because it is so infinitesimally small. So from now on, within this course, we're going to consider that mass to be 0. We're not going to do 1 divided by 2000 every time we talk about electrons. And so electrons are going to be found outside the nucleus, okay? So they're going to be populating this outside space. And so we'll talk about sort of these different representations of atoms visually. A lot of folks know like the Jimmy Neutron like type symbol, where you have kind of like a cluster of something here, and then you have like these big sweeping sort of orbits. Okay, and so it's not the most correct, but obviously my donut over here isn't the most correct either. And so again, with science and talking about something that's so tiny and so small, we have to have some way to model these concepts to really kind of wrap our brains around what's happening inside. And so we'll talk about why this isn't super accurate, this isn't super accurate, and sort of what it takes to make an accurate representation of an atom. All right. So whenever we're talking about the periodic table, we are assuming that all the atoms, until they react, right, they're going to have no charge. And so they're going to be neutral. So atoms are not charged, even though they're made up of charged particles. Okay. And so in helium atom, we have our number of protons, neutrons, and electrons. And so how we're able to determine the number of that is going to be based off of the periodic table. Okay. And so here's again kind of a rough diagram of what it looks like inside of a helium diagram. For the protons, you can see in the center, it kind of looks like those light colored berries, I guess you could call it. And so we see that they have 2 protons. And then we see for electrons, again, it's in this outside space, so outside of that nucleus, we have 2 of those guys. And then for our neutrons, which is going to be like the dark berries in the center, we also have 2 of those. And so you might be wondering, why is it 2, 2, 2, right? And so I'll give you a hint. It has to do with something with atomic number. So you can see kind of lightly in the background here on the periodic table, we see helium is atomic number 2. It has 2 protons, it has 2 electrons. And it just so happens we do have 2 neutrons, and we'll talk more about how these things might change in number depending on the situation. And so here's another kind of close-up version of that helium model. And so this one, we have those orbits, okay? And so we can see that same pattern. We have those 2 protons, we have 2 electrons, and we just so happen to have 2 neutrons. And I, not to scale, just so you know, atoms are not this big. I didn't know if you knew. And so technically what a actual helium atom is going to look like is like this. So we kind of view things instead of those like very discrete and like very precise like orbital lines. It's actually more like a cloud. And so we call this the electron cloud. That was termed before cloud technology. So fun fact there. And so in the cloud, we have electrons that are constantly moving and whizzing about, and their energy can vary depending on a situation. And so just like how we talked about noble gases, so they're the popular girls all the way to the right of the periodic table that are very stable and unreactive. And so we have to put energy into this cloud to be able to move those electrons in a way that they wouldn't naturally to create the effect. And in the case of neon, to create neon lights, which is pretty cool. And so, yeah, we have a kind of a rough estimate. The darker the cloud is, the more of a chance or possibility electrons can be found there. And obviously, as you kind of get further and further out, you can kind of see how it dissipates. And so that means there's less likely of a chance to find electrons within that part of the cloud. Okay, so let's go ahead and take a short break. So if you want to get up, stretch, walk around for a second, please do. All right. So we talked about our electron cloud and kind of the rough estimation of where these electrons are going to be held. And so to go back to, where these guys are located, they're going to be outside the nucleus, okay? And so it was thought that electrons existed in rings like planets rotating around the sun, but that is incorrect. Okay, and so again, at the time that these types of models were being used, This was our best way to visualize atoms at the time. We will be using this type of modeling for the time being, just to kind of introduce you to the basic concepts of atomic theory until you get a little bit more comfortable. We'll talk more about those more advanced models. But for the time being, this sort of like celestial, planet-like movement is helpful to get us started. And so this is a good way to show the energy level of the electron, and we'll do that much later. And so when we talk again about energy, think back to our noble gases. If we input energy in the form of electricity, we get those gases to light up. Okay, so here are the location of electrons. And so we see that this is nitrogen. And so nitrogen has 1, 2, 3, 4, 5, 6, 7 protons. And presumably, that looks like 5 neutrons. Yeah, I can't see that. But we do have 7 electrons. Okay, so that matches the number of protons. Interesting. Okay, and we're going to see that pattern. And so going back to talking about the cloud, we can never know the exact location of an electron because they are in constant movement, right? If you think back to our vibrating tables on that very small scale, and that's because of those whizzing electrons, okay? And so a great example to think about it is think about fan blades, right? When everything's completely stopped, you can say, well, this blade is in this position, this blade is in this position. But once that fan turns on, it's very difficult to sort of pinpoint and keep track of that movement of individual blades, which is a great way to think about the ways in which electrons move. If you've ever seen the TV show Breaking Bad, the main character takes on an alias called the Heisenberg principle. And so that is what is kind of describing this phenomenon, is we can't really know the speed and the location of an electron at the same time. Speed, also known as velocity. And so electrons are very tricky things to kind of pin down. And so it makes it even more incredible that we know so much about them, even though they're kind of fast little speedy guys. All right, so now we're really getting into the meat and potatoes of atomic theory here. And so we are going to talk about atomic number. So every element has its own atomic number. Okay. So atomic number is equal to number of protons, which is equal to identity. Okay, this is really important. And so if I ask you, what is the proton particle? You say the identity particle, okay, the identity. And so this acts kind of like a barcode or like a name, like a way in which to reference the elements. And so the number of protons is always going to stay the same. Okay. And so what I mean by that is, if we go back to our PowerPoint here, for sodium, okay, we're going to say, all right, so an elemental symbol is Z, and then we have our atomic number, and then we have our mass. So let me bring this back up here. And so the example we talk about is potassium. Where'd you go? There we go. Oh, there we go. So we have this elemental symbol Z. So this is our elemental symbol. And so this is like when we look at the periodic table, we see C for carbon, N for nitrogen, H for hydrogen, Fe for iron, Hg for mercury, etc. Okay, so that's what I mean when I say elemental symbol. And so usually how we express how many particles we might have is usually in this setup where we have atomic number, okay? And then down here, we're gonna have a mass value, which we'll talk about what that is composed of in just a moment. And so the example we're gonna look at is going to be potassium. So potassium is the most passive aggressive element. Oh, just kidding, not potassium. It's because I saw the bananas. So I instantly was like, oh yeah, we're gonna do potassium. Just kidding, sodium. Sodium is not that passive aggressive. It's a little passive aggressive because it says nah. And so if we look at the periodic table, we see Na, it's kind of hard to see, but here in the background, we see Na is gonna have an atomic number of 11, okay? And so, yeah, Na with an atomic number of 11, perfect. And so there's a couple assumptions that we can make about Na. And so we know for hashtag fact, because of our info up here, that sodium has 11 protons. And because we're assuming that all elements on here for the time being are going to be in a neutral state, meaning they're not charged. So neutral, not charged. Okay. We are going to have the same exact number of electrons. Okay. And I'll show you why that is in just a moment. And so when we think about protons, we saw that they are positively charged, and then electrons, they're negatively charged. And so when we are talking about something being neutral, okay, and not charged, right, that means our number of positive charges has to be equal to the number of negative, okay? And so that's why we can make that assumption, is if we're just looking at the periodic table, we're not talking about reactions or anything in solution with one another. We assume that everything is neutral, okay? It doesn't have a charge. And so that means protons is going to equal the number of electrons. Protons equal to electrons. Protons equal to electrons, as long as it's in a neutral state, okay? Oh, it does have potassium. And so another good example is looking at potassium, which is super passive aggressive. We look at the periodic table here, we see K, no punctuation, and we see that it does have an atomic number of 19. So if we move down just a little bit, we see that we have K, atomic number 19, okay? So we're going to assume it is neutral and not charged. And so as a result, we have 19 protons and also 19 electrons. Okay. And so let's go ahead and do a quick little try it. And so we're gonna find the number of protons and electrons of 3 different elements. Okay. Not discussed. So completely new elements. And so give it a shot, take a look at the periodic table, look for atomic number, and then assign how many protons and electrons belong to those 3 different elements. Okay. So we see in potassium, this is going to be a similar model that we looked at before. And this has a name, it's called a Bohr's model. Hopefully it's not too boring. Do you get it? Do you get it? Okay. So we just finished decorating our guest room, which is where I've been sleeping during this time, just because the treatment has been really intense, and I haven't been able to like really sleep right, and I like am up all night and like pacing and needing to do something. And so to not drive my wife crazy and keep her from sleeping, and so not being rested for work, I was sleeping in the guest bedroom. And so yeah, we just got it finished. And so my wife's dad was over today to help us out with some stuff around the house, and he saw the guest bedroom and he was like, I just need to start a fight with your mom so I can just like come stay with y'all. Obviously they're not those types of people, but it's just funny, like that's how much he really liked the guest bedroom. And so that's what that text exchange was, just so you know. Yeah. The plus side about not having to sleep next to my wife, which is sad, is being able to cuddle with Winnie. My wife and I are both very allergic to dogs, but her way more so than me. I grew up with dogs, and so it's been really nice to take advantage of cuddling with little Winnie, which is good. So if there is a silver lining to this. All right, and so this is our Bohr's model. We can see that we do have 19 protons. And if we were to count all these electrons, so the little blackberries with the negative sign through it, we would count 19. I'm not going to do that now. You can knock yourself out, have fun. But we can see the number of neutrons is 20. And so it doesn't match. And so let's talk a little bit more about these. And so now that you know how to find all the atomic numbers for each and all the elements, you can find the atomic mass. So we can use this chart as a guide. And so we have our proton and neutron coming in at 1 AMU. Again, that's atomic mass unit. And so those are going to be the units we are going to utilize for the time being. And so just like if you were to say like 10 ounces or 8 pounds, or you know, something in metric, because metric is so much better. So like a kilometer. That's what AMU is going to stand in for, is that unit. And so for the mass for electron, we're going to consider that 0 because of how small it is. And then we have our 3 charges here. And so to find atomic mass, we're going to have the mass of the protons plus the neutrons. And so going back to talking about how the nucleus is very dense, so it's a lot of mass in a very small area, this is why. And it's because all the mass, as we saw on the chart on the previous slide, is all attributed to just the protons and neutrons, because electrons are, you know, effectively 0 AMUs. And so the bottom number of our elemental symbol. So if I bring this back up, okay. Ooh. Hang on. There we go. Wait, nope. Sorry, let me see if I can reshare my iPad here. There we go. Okay, so if we go back to our elemental symbol here, we talked briefly about mass, which is right here. And so that is going to be where our mass number is. I do want to note that on the slide here, okay, it shows 22.99 as the mass. And so we'll get into why this is a decimal, but for the time being, all of our mass numbers are going to be whole numbers, okay? And so for our intents and purposes, so for sodium, we know there's 11 protons because the atomic number of 11 plus 12 neutrons gives us an atomic mass of 23. So that's the whole number. And so that's how we're able to calculate. And so go ahead and determine the number of protons, neutrons, and electrons for argon. Like during the pandemic, all hopes are gone or something like that. I don't know. I'm insert terrible joke here. And so, okay, so if we look at argon, so she is one of the noble gases. So she's on the right-hand side of the periodic table over here. She has an atomic number of 18, an atomic number of 18. If we really wanted to know the mass of argon, we would have to pull up another periodic table. I'm just going to like Google. No, that's not helpful. Okay, let's go ahead and use this guy. Cool. So if we look at the periodic table, oh no, wait, or of course I picked the periodic table that has the noble gases cut out. I'm just trying to find one that has the masses on the bottom. There are some really cool like shaped periodic tables. Ah, there we go. So we can see argon up here, atomic number 18, it is showing a mass of 39.948. And so just for this particular exercise and the exercises we're going to be doing for atomic theory, we're going to round that up. We usually should not, okay? And we'll talk about that later this presentation about why that is, okay? And so we're going to say for now, argon is going to have an atomic mass of 40. And so how we calculate the number of protons, neutrons, and electrons for argon, we are going to need that number 40. So let's go back in here. And so if we scroll down a little bit, okay, we know that good old argon, okay, has an atomic number of 18, and then we're going to go ahead and say a mass of 40. And so to find protons, what do we do? we look at atomic number. So protons, we are going to have 18. For electrons, what do we do? Okay, so assuming a lot of things you shouldn't assume, but in this case, it's okay. Assuming a neutral atom, okay, it's going to be the same number. And then for neutrons, we're going to need to get a little creative, right? So we know from our previous slide that protons plus neutrons equals mass, right? And if we only have mass and protons, okay, we've got to work a little bit backwards. So think about how we would rearrange this equation to then give us what we are looking for, which is going to be the number of neutrons. Okay, so what we need to do is we need to take our mass. Okay, we're going to subtract the number of protons to give us how many neutrons we have. And so in our case, we are going to take 40. We're going to say minus our 18, and that's going to give us 22. And so da 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 da. So that is going to be how we do our calculations for these three different particles. Okay. So, and what do you know? We have 19 protons and 20 neutrons. What is this? Who is she? Oh, this is for potassium. Oh, that scared me. I was like, did I not know how to do math? Okay. And so we'll talk about isotopes next class. We'll have a homework just with like calculating these different subatomic particles. And yeah, just kind of get used to using the words protons, neutrons, electrons frequently. And yeah, hopefully it won't be too weird talking about these little things inside of really little things that make up everything, hopefully. Again, thank you so much for your understanding and your support. I've gotten some messages from y'all supporting me, and I really appreciate that. I miss y'all a lot. I hope you know I mean that, and I hope I'm able to come back soon and have some solution for what's going on. But again, remember, knowledge is power. Thank you all so much for everything, and see you soon.